Okay, welcome to discussion here. We're going to continue lecturing on nomenclature where we kind of started last week. And again, with the exam today, which want to kind of finish up that topic at least. We're kind of halfway through, I believe. Okay, so last time when we were talking about sort of nomenclature, we continued on. We talked about really type 1 and type 2 compounds. A reminder that really both of those type of compounds are ionic compounds. And again, this is from chapter 5, I believe, or 6, chapter 6, I believe. So when we have an ionic compound, as a reminder, that is always between really a metal and a non-metal. And whenever you have that combination of two things, really the most important one, as we talked about, is always the metal. And really the location of where that metal is on the periodic table really kind of determines how you go about naming them. So a reminder that basically if it's a metal that has a fixed charge, it will be somebody from group 1, group 2, group 3. It will be zinc, cadmium, or silver. All those guys have basically fixed positive charges. And when we have those are considered type 1 compounds, which means we use the whole name of the metal for type 1, which basically will be these guys. Type 1. And we use the whole name of the metal. And again, that non-metal, we kind of dropped the last part of the name and put IDE at the end of it. Again, no Roman numerals or anything basically needed in that particular case. When we do get a metal, though, that is really, as it says here, in the transition metal region of the periodic table, are just to the right, things like lead, tin, antimony, bismuth, and that sort of area of the periodic table. Again, that is sort of below the staircase, but just to the right of the transition metals. Those guys as well, they do need Roman numerals. And remember that Roman numerals are for really type 2 compounds, which again is a metal, non-metal, where the metal is the most important thing. And here, the reason we use a Roman numeral is because the metal has the ability to make more than one type of charge. So for example, iron in certain cases can be +2. In other cases, iron can be +3. So because it does have the ability to make a variable type charge, when we name it, we do have to sort of indicate to the person, whoever's looking at the name, that, in this case, we're talking about iron with a +2 charge or iron with a +3 charge. And remember that the Roman numeral, when you do that, and when we do type 2 naming, we basically use the whole name of the metal. We use that Roman numeral. And again, this is the positive charge on the metal, not how many you have of it. So the Roman numeral. And then we use the non-metal like normal with the IDE at the end of it. So the good news is, as we talked about last time, you will always know what the charge is on the negative guy or the anion that's attached to the metal. But and then you could kind of work your way backwards to figure it out. So, for example, I believe we saw, speaking of iron, if we had something like FeO, and we would look at this and go, that is iron. It's a transition metal, could have multiple charges, but for sure I know oxygen there is group 6, has a -2 charge, which means in this case, the iron would have a +2 charge, and the name would be iron Roman numeral 2, again for the charge, and it would be oxide at the end. And again, that would be different than if we had something like Fe2O3, same two elements, iron and oxygen, but a little bit different here. We have iron. Again, we're not sure what the charge is, but we also have two of them in this particular case. We do know the charge on one of these oxygens is -2, and there's 3 of them, which if we just draw it out, we can count up all the negative charge equals -6. Remember that when you put together something that's positive and negative, you want to make sure that the overall charge is 0. So in order to balance out the -6 from the oxygens, each of these irons here would have to be +3. And that gives you obviously a +6 if you add them all together, balances out the -6. In terms of the name here, this would be iron Roman numeral 3. Again, 3 because of the charge. And even though there are multiple oxygens there, it has no effect on the name, and it is just oxide. Any questions on those type of naming that we talked about previously? Okay, so continuing on with naming here. Let's take a look at each of these and again, kind of go through the names and see, what we're looking at, what we should be looking at. So obviously, if we see this MgBr, first off, we do want to identify what we're dealing with. So Mg is a metal, Br is a non-metal. So automatically, when you see that, we should know that this is an ionic compound for sure. And it always is with a metal and a non-metal. And as we've talked about previously, it is really the metal here that is the most important one to look at. We look at magnesium, we look at the periodic table. We see magnesium is group 2 on the periodic table. That means it has a fixed charge, which means that this is basically a type 1 compound. And that means that really all we have to do is use the whole name of the metal and put IDE on the back end of the non-metal. And this would be called magnesium bromide in this case. We again do not need a Roman numeral. And we would end up with magnesium bromide in this particular case. It is made up. Remember that when we look at an ionic compound such as this, although we never want a charge in the actual compound formula itself, it is made up of 2 things that do have charges. In this case, the cation, which is the positively charged ion, would be a magnesium that's carrying a +2 charge. The anion, which is the negative guy in this particular case, would be Br minus. Again, Br carrying a -1 charge. Remember that this 2 is not part of the anion formula. The 2 means that you have 2 of these Br minuses. So sometimes people, when they're asked to write perhaps the formula for the anion, they'll write like Br2 minus or something like that. And that actually is incorrect. Again, the 2 here means that you have 2 separate negative ions that are there. Any questions on that one there? Same thing here. If we look at this, that is lithium, which is a metal. That is oxygen, which is a non-metal. Again, that's going to tell us it's an ionic compound. Again, we're going to look at the metal, which is lithium. That is group 1, which means it has a fixed charge. That tells us it's a type 1 compound. And really, that's all we need at this point. We would use the whole name of the metal, which would be lithium. The oxygen ends in IDE, so this would be lithium oxide. Again, the 2 here has no effect on the name. And we would end up here with lithium oxide. This particular one, again, made up of a cation that has a +1 charge and an anion that has a -2 charge. And that, again, is really why there is a 2 here in the formula, because we really need 2 of those lithiums, each with +1, to balance out the charge there on our oxygen. Lastly, on this one here, we have CrF2. Cr is chromium. That is a metal. F is fluorine, which is a non-metal. So again, tells us it's ionic. We look at the metal, which is chromium. And if we look in chromium on the periodic table, we see it's in a transition metal region, which automatically really tells us it's a type 2 compound. That means that we really do need to sort of figure out the charge there on the chromium. So although we may not know what the charge is right now, we would then look at the non-metal, which is fluorine. And fluorine is group 7, which means it's fluoride. -1 charge, and there's 2 of them, which means overall negative charge is -2. Again, to balance this out to 0, the chromium would have to be +2 in this case. And this would be a case where we would need the Roman numerals. This would be chromium Roman numeral 2 for the charge. And again, even though there are 2 fluorides, it has no effect on the name, and it would just be fluoride. Whoops, fluoride at the end there. So this would be chromium Roman numeral 2 fluoride. And again, the 2 for the charge. And again, even though we have 2 of those guys, no effect on the name. Any questions on any of these here? So here's just sort of a decision tree between type 1 and type 2. And again, really, it is that positive guy or the cation that's really most important. Again, if you have a type 1, you can just pretty much roll right into naming. If you have a type 2, again, you need to kind of take a second to determine the charge on the metal. Use the Roman numeral as well to incorporate that. Remember that if you're working backwards, like we also talked about, if you had something like magnesium oxide and you want to write a formula, again, the best thing to do is just take the simplest representation of that. So magnesium is group 2, which means it has a +2 charge. Oxide is oxygen, which is group 6, means it has a -2 charge. So when we put those guys together, we really just need one of each of those guys to balance out the charge. And our formula would be magnesium oxide, or MgO. If we had something like copper Roman numeral 2 oxide, again, this name gives us information. The copper is Cu. The Roman numeral tells us it's a +2. So that's what the Roman numeral again tells us. In this case, oxide is oxygen, which is group 2. And again, here, if we were to put this together, CuO would be what we would look for. Any questions on type 1 or type 2 in terms of naming? Again, you need to be able to name. You need to be able to go from name back to formula. You need to be able to write the formulas of cations and anions. Remember that when you write the formulas of the ions, they should have charges. That's why they're called ions. So they should have some type of charge included with it. Any questions on any of that? Then we're going to talk about another type of naming, which is type 3. And type 3 naming is a little bit different. It actually involves covalent bonding. And covalent bonding, as we've talked about previously as well, is a little bit different than ionic bonding. It is actually between 2 nonmetals. And the major difference between ionic bonding and covalent bonding is here we actually have sharing of electrons. And that sharing may be equal, that sharing may be unequal, but there's some aspect of sharing that's happening here of electrons in a covalent bond. And that's different than an ionic bond where we have a complete transfer of electrons from the metal to the nonmetal. How do we go about naming these? Well, honestly, these really are, I think, the easiest to name and to work with. But with that being said, they also are the ones that people really do sort of screw up the most. And I think it's because people think they have to do all kinds of weird things with these, and you really don't. People oftentimes, when we talk about type 1 and type 2, I mentioned that people like to try to use like prefixes and stuff like that. But actually here in type 3 is really the case where you should use prefixes. So we go about sort of naming these guys like this. The first element in the formula, you use the whole name of the first element. The second element in the formula gets kind of like the non-metal treatment with IDE. And now this is really, we use the appropriate prefix with the whole name, and we use the appropriate prefix with the non-metal part. So this is really the ones that actually use prefixes when we name them. Prefixes like obviously mono means 1, di means 2, tri means 3, tetra means 4, penta means 5, hexa, hepta, we'll see a chart here in just a second, octa, nona, and deca. And there's a couple of rules and considerations that we do when we use these prefixes. The first one is pretty simple. The first one is the prefix mono, which means 1, is never used on the first name, but it is okay on the second name. So mono is not used on the first name, but okay on the second. And the other main thing that we run across when we use these prefixes in terms of naming is occasionally when we use the prefix, we get a couple of vowels that back up to each other. So for example, we may get 2 O's that back up from each other. Like if we had mono and oxygen that came together, monoxide, we typically will drop the O from the prefix, and this would be something like monoxide. Also, like an A and an O is another very common one that we sort of get rid of. So instead of tetraoxide, again, we get rid of the A off of the prefix, and it's tetraoxide here, or tetraoxide. And those are some considerations. Oddly, usually a couple of I's together are okay. Like if you have diiodine or something like that, that's okay. But these are the two main ones, kind of 2 O's together, get rid of one of the O's. An A and an O, we typically get rid of the A. And here are the prefixes. Again, 9, by the way, we don't really see too much, is nona, and 10 is deca. And again, as I mentioned, we do get rid of some of the prefix vowels, especially when we get 2 vowels that sort of back up to each other. The nice thing about nonmetals and prefixes and type 3 compounds are essentially there's no worry about balancing out charges, figuring out what the charges are of everybody. You simply just need to count how many of each element you got, use the appropriate prefix, and that's it. There's nothing to balance, no charges. And again, that's why it's relatively easy, these guys. But again, sometimes it is ones that, sometimes people do mess up. So again, here's some examples of what I was talking about. We do get rid of that A, we do get rid of that O. And again, these would be sort of the proper ones. There are still ones that are compounds that we do use just the common names for. And here's 2 really important ones. Water, again, is H2O, not a refreshing glass of dihydrogen monoxide. Nobody wants that. So again, if you do see H2O, it's not a trick question. It is water. NH3 is ammonia. And one you could add to this list is CH4. CH4 is the simplest organic molecule you could have, which is methane. So these guys really should kind of go by their common names. You shouldn't use kind of type 3 naming for these guys: water, ammonia, and methane. So we have I2O7. So again, let's kind of take a look at these and see what we're dealing with. So when we look at this, we see I, which is a nonmetal. We see O, which is a nonmetal. That tells us that's 2 nonmetals. And that automatically should be really happy because that tells us it's a type 3, which basically means we just need the proper prefixes. Not worried about any type of charges or anything because there is no charges. So 2 prefix is di. 7's prefix there is hepta. And again, we use the full name of the first element, which is iodine. The second element gets the IDE at the end of it, which is oxide. And now we just simply put these guys together and we end up with diiodine heptoxide. Again, here, the 2 I's backed up to each other are okay, but we did drop the A off of the prefix because that A and O not so good. Again, really nothing to balance other than just to see what is there. If we look at this, again, we see carbon, which is a nonmetal. We see oxygen, which is a nonmetal. Again, that tells us that's two nonmetals. That tells us it's a type 3 compound. There's only one carbon, which means the prefix would be mono. There are two oxygens, which the prefix would be di. Remember again here that we will use the whole name of the first element, which is carbon. The second guy gets the IDE. And remember that the one rule is mono is not going to be used on the first name. So in this case, we would just use the whole name, which is carbon. And then we would use the prefix for the second guy, which would be dioxide. So carbon dioxide here is our CO2. Any questions on that one? Lastly, here we have PCl3. Again, same sort of game plan. P is a nonmetal. Cl is a nonmetal. Again, telling us that that is type 3. And we are going to use our prefixes here. We again see 1 here, which means mono. 3 means tri. Again, we would use the whole name of phosphorus, and chlorine would become chloride. And much like above, we will not use mono on the first name. So this would be phosphorus trichloride. Again, nothing to balance or anything like that. Just simply telling everybody how many of each of those guys we have. Any questions on those? I want you to try a couple here. Let's do dinitrogen pentoxide. Let's do carbon tetrachloride. Let's do dioxygen hexasulfide. So write the formula for these guys here. And then let's do NO2. Let's do P2N5. So give the name for these guys I just made up and give the formulas for those guys on the right. So take a minute or two, see what you come up with. Look here, and again, like I said, these are really the sort of easiest ones out of all of them. You just don't want to overthink it. So when you look at this first one here, we'll look at this guy. We have nitrogen, which is a nonmetal, oxygen, which is a nonmetal. And at that point, it should kick you off that this is a type 3 guy. I should be using prefixes. And again, the nice thing about that is simply you just need to write what is there. So I see 1 nitrogen, prefix for 1 is mono, but we don't use it on the first name. So we just simply use the entire first name of the element there, which is nitrogen. There are 2 oxygens, prefix for 2 is di. And again, the oxygen gets the IDE at the end of it, so nitrogen dioxide. Here again, we look at phosphorus, which is a nonmetal. Nitrogen, which is also a nonmetal, again, tells you it's type 3. So prefix here is 2, which means that would be di. And again, the whole name there of the nonmetal, which is diphosphorus. Prefix for this guy is penta for 5, and nitrogen becomes nitride, IDE. So again, simply the prefix, whole name of the first element, prefix, IDE on the second. Any questions on those? Now, really, the simplest of them all is, I think, going actually this way, going from the name to the formula. As soon as you see some prefixes in these names, that's pretty much it for you. You don't have to really think about too much. There's nothing to balance, no charges. Di means 2, nitrogen means N, so N2. Penta is 5, oxide is oxygen, and you just write N2O5, and you're done with this particular one. Carbon, although I don't see a prefix, I do see a prefix here, which is tetra. That then tells me that really the prefix here is mono, which means one, and carbon, which means I really just have a carbon. Tetra is 4, and chloride is Cl, and it would be CCl4. Again, nothing to balance, no charges to deal with in this type of naming. Makes it relatively straightforward. Dihydrogen, again, I see prefixes. I see hexa. Di is 2, hexa is 6. So dioxygen means an oxygen with a 2. Hexasulfide, sulfide is sulfur with a 6, and that would be your correct formula there for whatever I just made up there. Might not exist, but I made it up. Any questions on type 3 compounds? Again, this is really the only place where you should be using prefixes is with type 3 compounds, nonmetals and nonmetals. At no point with type 1 or type 2 compounds that we talked about earlier, which are ionic, do we use prefixes. This is the only place really you should be using these prefixes. Any questions on that? Okay, then the last sort of naming that we're going to talk about will involve polyatomic ions. Here's a review of what we talked about. Again, type 1, fixed charge metal. Type 2, variable charge metal. Type 3, no metals at all non-metals, basically sharing electrons. Here's a decision tree as to where to go. So what are polyatomic ions? Well, polyatomic ions are really groups of nonmetals that are together. And they are kind of strange in the sense that they are groups of nonmetals that are actually held together by sharing of electrons, but they actually do have a charge. So they're considered ions as well. So a couple important things about that is obviously, for example, here, if we look at this guy here, NH4NO3, and we split it right about there, this actually contains 2 different polyatomic ions, NH4 plus, that 1 nitrogen and 4 hydrogens all stay together because they're basically sharing electrons. Those are nonmetals, they're covalently bonded together, but the overall unit here does have a +1 charge. So we would never break apart the nitrogen and the 4 hydrogens separate from each other. If this thing moves, it moves as a whole unit, everybody together. Same thing over here. This is a nitrogen and 3 oxygens that has a -1 charge. Same deal here, that nitrogen and 3 oxygens are covalently bonded together. They're sharing electrons. They move around as a whole unit. Each of these things have a special name. This is what is known as the ammonium ion, not to be confused with ammonia that we just saw, which is NH3, no charge. This is the nitrate ion. And pretty much if we put both of these together, this guy here, NH4NO3, would be called ammonium nitrate. So to give you just sort of a visual representation of sort of what is going on here, that nitrogen and those 4 hydrogens are again sharing electrons. So the hydrogen and the nitrogen all sharing electrons. And again, that's why this whole thing has a +1 charge and it does move around as a unit. That nitrate also sharing electrons. And again, this entire thing has a -1 unit. And really with polyatomic ions, we really do treat them very much kind of like type 1 or type 2 compounds usually. But basically, it is still the positive and negative charge that we're putting together. So because it's +1 and -1, we just need one of each of those to balance it out. And that's why we do see the formula that looks like this. As we will see, pretty much NH4 plus is the only positive polyatomic ion. So for the most part, a lot of times these polyatomic ions are negatively charged. and they will be attached to a metal. And that's why I say a lot of times we use kind of type 1 and type 2 rules with them. And that means that, if we have a type 1 metal, we would just use the whole name of the metal and the whole name of the polyatomic ion. So if we have sort of a type 1 situation with a polyatomic ion, just like we did with type 1, whole name of the metal and whole name of the polyatomic ion, which we'll take a look at a table here in just a second and some more. If you have a type 2 metal involved with a polyatomic ion, we do the same thing. We use the whole name of the metal. And just like we did with type 2, we will need a Roman numeral for the positive charge on the metal. And then we just use the whole name of the polyatomic ion. So they're named very similar to how we kind of name things for type 1 and type 2. In addition, if you have multiple polyatomic ions, just like, for example, we had, Na, or not Na, we had like FeBr3. That Br3, that 3 had no effect on the name. Same thing with our polyatomic ions. If you have more than one polyatomic ion, it will have no effect on the actual name. So you just call it what it is, even if you have one of them or two of them or three of them in a particular formula. Any questions on that so far? All right. So let's take a look. So this is a table of some polyatomic ions. And, you do need to know the formulas and the names because it's going to be important to be able to balance out the charges. And there's a good way to sort of remember some of these or look at some of these, and that is to sort of group them by ones that are related to each other. So for example, here, if we look at NO3 minus and NO2 minus, those two are related to each other by the number of oxygens. One has 3 oxygens, one has 2 oxygens. Each has a -1 charge. The one with 3 oxygens is nitrate. The one with 1 or 2 oxygens is nitrite. When we look at, for example, SO4 2 minus, which is down here, and SO3 2 minus, these two guys are related to each other. The only difference is the number of oxygens. One has 4, which is this guy. One has 3. They both have a -2 charge. The one with 4 oxygens is sulfate. The one with 3 oxygens is sulfite. So typically in a group of 2 that are related to each other, they typically will end in ate or ite. 8 is the one with the most oxygen in that group. And ite is the one with the least oxygen in that group. And that's a really good way to sort of memorize it. There are sort of groups of 4 that are related to each other, like we see here, actually. This is ClO4 minus, ClO3 minus, ClO2 minus, and ClO minus. Every single one of these guys have a -1 charge. The only difference between all of these guys are the number of oxygens. Guy on the left has 4 oxygens, guy on the right has 1. So in a group of 4 that's related to each other, you could kind of break it up in half there, right about here. And if we look to the right, these have the least number of oxygens, which means they should end in ite. So this would be chlorite. This guy over here would also be, let's write down here, chlorite. Obviously, they both can't have the same name. So when we have a group of 4, the one with the least number of oxygens in that group of 4 will end with ite, but we'll also start with hypo. So that is hypochlorite. Then the one with the second least oxygens is chlorite. Same thing if we look to the left, they have the most oxygen, which means this would be chlorate, ATE. This would also be chlorate. Again, same idea. We cannot have obviously two names for two different things, or same name for two different things. So the one in a group of 4 that has the most oxygens will also start with per. So that's perchlorate, chlorate, chlorite, and hypochlorite. And if you look at this, this is a Cl, which is a halogen. You could actually swap out the halogen for any of the halogens, and they're named similar. So let's just say we had BrO3 minus. Instead of chlorate, this would be bromate, AT. So again, we could swap that out for iodine as well. It would be iodate and so forth. Other common things that you see on this table is, for example, right here, this is CO3 2 minus, which is carbonate. And between the top guy and the bottom guy here, we added an H plus. And when we added an H plus, it becomes hydrogen carbonate. And sometimes hydrogen carbonate, instead of saying hydrogen, they use the word bi, like bicarbonate, like antacids. The charge does change because we add a hydrogen and a +1. So -2 and +1 leaves us a -1 overall. So the charge does change as well when we do that. Although a vast majority of everybody on this table or these polyatomic ion tables ends in ite or ate, there are some that still end in IDE, like OH minus is hydroxide. Another one is CN minus, there it is right there, is cyanide. So there are a few that do end in IDE, but a vast majority will be ate or ite. Again, the best way to do this is to sort of learn them. So sometimes people will learn, all the eights and know that the ites are 1 oxygen less. The charge, everything else stays the same. Or sometimes people will learn all the ites and know that the eights would be 1 oxygen more, and everything would stay the same in terms of charge. Here's another table and another one with some other ones on it as well. Again, you can see here's azide, which again ends in IDE, and some of the other ones. So let's talk about, how we go about naming these, because really, as I mentioned, that ammonium, this guy right here, is probably your only sort of positive guy that you'll come across. We typically will see these guys hooked up with metals. So for example, if we had NaNO3, when we look at this, we would break this apart and we see here that is sodium, which is +1. That's a type 1 metal, which means we would follow type 1 rules, which means we would use the whole name of that, which would be sodium. We would recognize this hopefully as nitrate, which is NO3 minus. And where did that go? Right there on top. And we would use the whole name of the polyatomic ion, which would be nitrate. So this would be sodium nitrate. If we had something like Fe NO2 3, when we look at this, this is iron, which is a type 2 metal, which means we're not sure what the charge is on it. So we do have to figure out, just like we did before, but when we look in the parentheses, we see NO2, which is really NO2 minus, and there are not one of them, but there are 3 of them. Remember that each of these guys are really only -1. So that's a -3, which means in this case, just like we did with type 2, we're able to figure out what the charge is on the iron, and it would be iron Roman numeral 1, 2, 3. And even though there are 3 of these guys here, we would call it just nitrite. Again, the 3 is for the charge on the metal. Question on that there. You might also notice that I did put parentheses around my polyatomic ion, and you should put parentheses around your polyatomic ion when you have more than one of them. So for example, if I wrote it without the parentheses, I would end up with something like this, which would imply that I had 23 oxygens, which is clearly not the case. So whenever you have more than one polyatomic ion, you do need to put parentheses around it and the number on the bottom. Any questions on that there? All right, let's do a few here to finish it out in terms of our naming. Let's do Li2SO4, give the name for that. Let's do Cu HCO3 2. Let's do BaOH2. So give the names for those, and then let's do some names to formulas. Let's do iron 3 phosphate. Let's do ammonium sulfide. And let's do magnesium perchlorate. All right, take a couple of minutes here. I know we're a little bit over. We're just going to finish these last couple of samples and we'll be done with the naming. So see what you come up with if you could hang out. Okay, so let's take a look since we already in the end here, or we passed the end. Let's finish it up here. So again, we want to just approach the same way. Like I said, probably 9 times out of 10, you will see probably those polyatomic ions attached to a metal. So we just want to identify what we got going. So obviously lithium is a metal. That is SO42 minus, which is sulfate. And this is lithium, which is group 1 and has a fixed charge. So because of that, again, it's going to be the metal that really determines the naming aspect of it. And because it's type 1, we again just use the whole name of the metal, which is lithium. And then the whole name of the polyatomic ion, which would be sulfate. Again, here, the 2 has no effect on the name. We shouldn't use any prefixes. Again, those are only for type 3. And the reason the 2 is there is to balance out the -2 charge from the sulfate. So we basically have 2 Li plus ions that are present. Any question on that name? Same thing here. If we look at this, this is copper. That automatically should tell us probably type 2 because it's a transition metal. Also should tell us that at this point, perhaps we're not familiar with what the charge is. We do see HCO3, and if we look down here, HCO3 really is HCO3 minus. And remember that all of those guys basically have a -1 charge, and there's not just one of them, but there are 2 of them. So again, if we just draw it out, we can see that the overall negative charge here is -2. And obviously to balance it out here, we would need a +2 on that copper. And that would translate to a name of copper Roman numeral 2. Again, for not how many coppers we have, but the actual positive charge. And even though we have 2 of these bicarbonates or hydrogen carbonates, again, it has no effect on the name. We would just call it hydrogen carbonate. Or again, you could just call it bicarbonate at the end if you would like. Any questions on that? So either copper to hydrogen carbonate or copper to bicarbonate would be the correct name there. Lastly, here we look at Ba, which is barium and a metal. OH is hydroxide, which is down here. This tells us it is a type 1 metal because barium has a fixed charge, which means that's pretty much all we need to roll into the name. We'll use the whole name of the metal. Even though there's 2 of them, we just use the whole name of the polyatomic ion, and this would be barium hydroxide. Any questions on any of those names? All right, so going from name to formula, we could use the formula to help us figure out what's going on. When I see iron Roman numeral 3, that automatically tells me I have an iron with a +3 charge. When I see phosphate, I would look on the table or at some point memorize it, and phosphate would be right there, which would be PO4 3 minus. Again, this entire thing has a -3 charge, which actually will balance out with our +3 charge here. That means we really just need one of everybody here, and we would end up with FePO4. As you can see here, you do not need to use parentheses if you have just one polyatomic ion. You could just put it in just like I did there. Again, only when you have more than one polyatomic ion do you need the parentheses. Looking at ammonium sulfide, ammonium again is one of the few positive ions you'll have, and that is NH4 plus. Again, although there's a lot of things there, it still only has a +1 charge. Sulfide IDE is actually sulfur from the periodic table, and that is group 6, which means it has a -2 charge. So here what we're putting together is +1 and -2. That means we actually need 2 of these NH4 pluses. Because we need 2 of them, that means we do need to put parentheses around them with a 2 on the bottom. That indicates that we have 1 and 2 of these guys. And we obviously have 1 sulfur here. So that would be NH4 2S. Question on that one there. Lastly, here we have magnesium, which obviously is group 2, which means it has a +2 charge. Perchlorate's one of those group of 3 guys right here, which is ClO4 minus. Again, this whole thing has a -1 charge. So when we put it together with magnesium, we need not just one of them, but we actually need 2 of these guys to balance out the charge. And that means when we put it together in a formula, Mg, because we have more than one of the polyatomic ions, we need parentheses, ClO4 and a 2 on the bottom. And that would be magnesium perchlorate. Any questions on polyatomic ions or naming polyatomic ions? Any questions on naming in general? That should wrap up all naming that we will cover in this class. And again, this is pretty much the stuff we talked about there, the table. Any questions on any of the stuff we just talked about here?